Hello everybody. I'm sorry not to be able to be with you. The organisers have asked me to open the conference by offering a personal view of the evolution of calculus as it was 50 years ago and as it is now. I've decided to broaden this to experiences since I first encountered calculus myself as a 15-year-old in school. I note that the conference is focused around four themes. A, the school-university transition with a focus on calculus. B, the fundamental theorem. C, the use of digital technology. And D, the teaching and learning in various disciplines. This will be a personal journey. It will touch on ideas that have fascinated me as we live through a lifetime that has seen and continues to see unprecedented evolution of digital technology. From such a vast enterprise, I seek an inner simplicity that gives human meaning to the mathematics of change and growth. Let me begin by taking you back to my first encounter with calculus as a 15-year-old schoolboy. If his efforts matched his enthusiasm, he could be a competent mathematician. This is my first report as a 15-year-old. My mathematics teacher was concerned that I spent too much time on a variety of activities and did not spend all my time on mathematics. This is still true, and it's why I wish to refer to a range of other disciplines in my presentation. I really enjoyed working from the calculus book by school teachers Durrell and Robson, published in the 30s. It defined the derivative as the limit of delta y over delta x as delta x tended to 0. Much later, for any real number dx, it defined dy to be f dash x times dx. Then, for dx non-zero, f dash x equals the quotient dy by dx. This is all based on Woodhouse's book from 1803, which introduced the Leibniz notation after more than a century using mainly Newton's approach. This spread to English-speaking nations around the world, including the American Mathematical Society, which based its organisation on that of the London Mathematical Society in the 1880s. Note the problematic meaning of the limit, where delta y over delta x could only be calculated for delta x non-zero, while the limit form involved putting delta x equal to 0. There were also multiple meanings of symbolism, such as f dash x being both a quotient and the symbol d by dx being an operation. It was even an operation that could be repeated to give d2y by dx squared. Then there was the meaning of dx in dy by dx, and in the integral, where it is spoken of as the integral of y with respect to x. Many problematic meanings still remain today. Calculus is still based on an informal limit concept. For instance, the US Advanced Placement Calculus speaks of four big ideas, starting with limits, then moving on to derivatives, integrals and the fundamental theorem, with the possibility of addition of series. The detailed curriculum focuses on concepts that can be tested. Meanwhile, maths education research is full of misconceptions that occur in learning. Digital technology offers new facilities for performing fast and accurate numerical calculations, for the manipulation of symbols, and also for drawing dynamic pictures that offer visual and conceptual meaning. My own work in the 1980s involved developing software called graphic calculus to visualize concepts. One program allowed the user to magnify part of the graph to see that, close up, familiar graphs look less curved and under high magnification they look locally straight. The derivative now is not introduced as a limit, it is the slope of the graph itself. It is possible to look along the graph to see the changing slope. It's possible to trace it with your hand, to feel it. It has human meaning. Another program plots successive lines of slope f of x plus c minus f of x over c on the graph for variable x and small fixed c to plot points that lie on the graph of the practical slope function for variable x. In the UK we call this the gradient function. In the case of f of x equals x squared, the practical slope function is 2x plus c. As c is taken to be small, the graph stabilises visibly to the graph of 2x. Local straightness means giving meaning to all standard derivatives. For instance, looking at the graph of 2 to the x and of 3 to the x, the slope of 2 to the x is below the original and 3 to the x, which is steeper, is above. Look for a number e between 2 and 3 where the slope function for e to the x is again e to the x. Seeking a polynomial approximation links the visual information to symbolic calculation to give a sense of how quickly the approximation converges and allows e to be calculated to 10 or more decimal places by hand. This links embodied visual meaning to the symbolic derivative. Wow! But it does not deal with the rules of differentiation. A new approach to symbolism is now available, as I will indicate later. Now we turn to integration and the fundamental theorem. In this case, I take a function such as sin x and keep the same vertical scale while stretching the horizontal scale. In this case, you can see that the graph pulls flat. Taking the vertical thickness of the pixel line as plus or minus epsilon, the idea of pulling flat embodies the formal definition of continuity at x. Given any epsilon greater than 0, we can find a delta greater than 0 such that stretched in a window which it has width x plus or minus delta, the graph lies in the pixel line f of x plus or minus epsilon. Let us look at this a bit closer. The area A to a point x on the x-axis with y measured up from the x-axis, this can be imagined to change by an increase dx in x. Then the increase dA in A, calculated as y times dx, is given as dA equals y dx. This is a useful idea that links the embodied action of drawing to the formal definition of continuity. But on the negative side, there are concerns about the meaning. Here, the product dy by dx needs to be interpreted as a number, which remains unchanged even though the visual area dA clearly looks different. In addition, there's still the problem about the exact value of dA being precisely equal to y dx. To respond to this, we need to look at the bigger picture. I suggest that calculus has two successive levels of sophistication. One is the practical level that involves visual representation and symbolic calculation in which a process approaches a limiting value. Then there's the theoretical level that involves informal definition and deduction, which focuses on the limit object itself. Analysis, on the other hand, is based on formal mathematics, using set theoretic definition and formal proof. Users of calculus essentially only encounter practical and theoretical mathematics. Calculus involves visual and symbolic aspects. Embodiment is physical and mental. It's visual and gestural. It involves thought experiments. Symbolism involves calculation. It involves taking processes and thinking of them as objects. It has multiple meanings. The practical limit is a process as closed as is desired, and the theoretical limit is the limit object. Embodiment suggests a limit visually attained, which is good, but the symbolism suggests that the limit is not attained, which is rather sad. Here I build my framework on the insight of mathematician Raymond Wilder, who used the anthropological term culture to study the evolution of mathematical concepts. He wrote, "A culture is a collection of customs, rituals, beliefs, tools, mores, and so on, called cultural elements, possessed by a group of people who are related by some associative factor or factors, such as common membership in a primitive tribe, geographical contiguity, or common occupation." He used a number of anthropological terms. Cultural stress involves a need in the community which requires to be resolved. Cultural diffusion refers to moving cultural elements between cultures. Cultural lag acknowledges that diffusion takes time. Cultural resistance occurs when a community opposes diffusion. Cultural stability involves maintaining a culture that seems to be working. How do these cultural aspects affect calculus? In the calculus, we have stress from different needs in different communities, stress from fast-changing digital technology, cultural lag in transmitting new ideas to communities that may not even be aware of them, resistance to new ideas competing with stability. A major cultural factor is the conflict between cultural stability and changing need, which underlies the so-called maths wars. Pure mathematicians seek formal proof. Users require theoretical mathematics involving limit objects or practical mathematics involving limit processes. The plan is top-down. The learning is bottom-up. How does this relate to how humans learn to think mathematically? It's insightful to understand how we interpret what we see. This is a cross-section of the eye looking from above, with the pupil at the bottom and the back of the eye at the top. On the right is a view of the central part of the back of the eye as seen through the pupil, which includes an area called the macula, which is about 5.5 millimeters across. This recognises visual detail. In the centre of the macula is a circular region called the fovea, about 1.5 millimeters across. This recognises high-resolution colour and detail through cells called cones. The fovea is only about 250 cones in diameter. We will see that this has a profound effect on how we read symbols and how our eyes follow moving objects. When we read text, the eye stops for a brief fixation to take in information through the fovea and shifts between fixations in jumps called saccades. Read some words on this page to sense your eye movement as it jumps along the line. I'll give you a short time to read a few words to sense this for yourself. Try some of the lines. Expressions are read in many languages left to right in chunks. For instance, the expression 1 plus 2 times 3 is read in that order. The meaning depends on the spoken articulation. If I leave small gaps between symbols, then the meaning can be made more precise as 1 plus 2 times 3 is 3 times 3, which is 9. 1 plus 2 times 3 is 1 plus 6, which is 7. These can be written more precisely using brackets. The principle of articulation can be used at any level to give meaning to the use of brackets. It is not a mathematical definition, but it does lead to meaning for the use of symbolic operations throughout the whole of mathematics. In a short overview, I don't have time to consider the detail. In papers on my academic website, I'll show how to extend it to give meaning to all symbolic expressions and how to read them in a simple way. How does your eye perceive motion? Place your finger in front of you and move it to the left and right. The eye makes an initial saccade to focus on it. Then it moves in a smooth fixation to follow it. This will happen if you move your head or if you keep your head still and just turn your eye. I'll wait for a short time while you do this for yourself. Now, imagine 2 points on a number line, one fixed and one moving. The brain naturally imagines constants and variables, including quantities that can become arbitrarily small. The intuitive foundations for calculus are built into the human brain. Magnifying a physical picture from a book thickens the lines. Scaling on a retina display can maintain thickness if it's programmed suitably. Highly magnified, the graph looks like a straight line. The notion of local straightness relates directly to the structure and operation of the human eye. Using a retina display, the practical slope function stabilises on the theoretical slope function. This gives a visual embodiment supporting local straightness, which switches attention from the practical limit as a process that gets as close as is desired, to the theoretical limit, which is the derivative as a limit object. It gives meaning to the derivative as a theoretical object. So we must ask the fundamental question, why is local straightness rejected in AP calculus? Cultural resistance over the centuries still operates today. As an example, consider the Greek common notion that the whole is greater than the part. This is self-evident for counting objects or measuring figures. But Galileo was found guilty of heresy for suggesting that the whole numbers are in one-to-one correspondence with the squares of whole numbers. Cantor realised that this property is the definition of an infinite set. This was met with hostility and cultural rejection and led to his mental breakdown. I pose this question: is this happening in calculus today? Let us consider the formal theorem that a complete ordered field cannot contain infinitesimals. This implies there are no infinitesimals in the real numbers. However, it does not imply that there are no infinitesimals on a number line, just as there are no irrationals on the rational number line. I can prove to you that infinitesimals must occur in any ordered extension field of the real numbers. Let K be any ordered field with R as an ordered subfield. Define an element x in K to be finite if it lies between two real numbers, A and B, and to be infinitesimal if x is non-zero and lies between t and minus t for every positive real number t. Then we can prove the following structure theorem. Any finite element x in K must either be in R or of the form c plus epsilon, where c is in R and epsilon is an infinitesimal. The proof is a simple application of the completeness axiom. Call elements in K quantities and elements in R constants. Then we have the theorem that any finite quantity is either constant or a constant plus an infinitesimal. For finite x, the unique real c that occurs is called the standard part, st of x. So, to see infinitesimal detail for infinitesimal epsilon, we can magnify the scale by an infinite factor 1 over epsilon. By defining the epsilon lens pointed at c for any c and non-zero epsilon to be m from k to k, such that m of x equals x minus c over epsilon. Define the field of view of m to be the set V such that x minus c over epsilon is finite. The optical epsilon lens pointed at c is mu from V to R, given by mu of x is the standard part of x minus c over epsilon. This gives a map from the field of view on the extended number line k down to the real number line. The original elements c, c plus epsilon, c plus 2 epsilon in k differ by infinitesimal quantities, but their images on the real line are visibly distinct. However, c plus epsilon and c plus epsilon plus 2 epsilon squared differ by 2 epsilon squared, and the optical lens maps them into the same point. I have no time to discuss further details. They're available in the latest edition of Foundations and Complex Analysis with Ian Stewart, where we updated books we wrote 30 or more years ago with my most recent developments. Furthermore, the ideas apply in 2 or more dimensions simply by using optical lenses on each component. An optical lens in n dimensions can use different magnification factors on each coordinate. For example, you can use the magnification factor 1 over epsilon on both coordinates to see local straightness. Or you can use a horizontal magnification of 1 over epsilon and a vertical magnification of 1 to see local flatness. I do not have time to discuss these details either. They're here to show formal mathematicians that infinitesimal ideas are a fully valid part of formal mathematics. Optical lenses belong in formal mathematics. The ideas can be visualized in practical mathematics in any program that allows embodied scaling on each coordinate. For instance, it can be done in GeoGebra. This supports the notion of infinitesimals as variable quantities, as envisaged in mathematical applications and visualized naturally by the human eye and brain. They can be imagined as objects in practical mathematics or arbitrarily small quantities in applied mathematics. This supports embodiment as a major powerful tool in making sense of mathematics in ever more sophisticated insights at all levels of mathematics. I've focused on how we think about calculus, in particular the roles of embodiment and symbolism, how our brain makes sense of dynamic change, reading text and mathematical expressions, how we can embody change through operations that become mental objects, through practical limit processes, theoretical limit objects, and formal limit definitions and proof. building up to the limit concept, not formally down. I've not included essential parts of my broader framework, for example, confidence, anxiety and so on, not only in mathematics, but in the operation of the brain. I have proposed the need to think about cultural resistance that may impede our progress. For a version of this talk with more detail and a broader framework in maths and in calculus, look up David Tall on Google for my academic website. Thanks for listening. Enjoy your conference, but don't forget to dream. You never change things by fighting the existing reality. To change something, build a new model that makes the existing model obsolete.